Greetings, everybody. Thank you all for joining. We'll be starting shortly, just giving a few minutes for others to join. Thank you. Hi, everybody. We'll be starting in a few, so in about 4 minutes. Thank you all for taking time to join. Yes, good afternoon, everybody. I hope you can all hear me.
We can hear you, Ronald. Go ahead.
Yes. Ronald, we can't hear you. Are you there?
Yes, yes. I hope you can hear me now.
Yes, we can.
Okay, I think, yeah, let's just begin. Maybe the other people will join us as we continue this webinar. Yes, first of all, I'd like to thank you all for making time for attending this webinar. I'll make a small introduction on my part and for the partners that we have today that will be providing this small presentation on the topic of the day. So I am Ronald Mwangi, part of the technical sales team for Amotech Africa. And just a quick introduction about our company. So Amotech Africa is a provider of premium test and measurement solutions, ranging in different fields from electrical to mechanical to instrumentation and lastly telecoms. We're headquartered in Kenya, but with offices in Uganda, Tanzania, Rwanda, Ethiopia, and a bit of presence also in other African countries. Yeah, so under telecommunications, we have solutions now for your fiber, for your copper test and certification, uh, brands being AEM, and we're also very proud to have our partner here for Anritsu, called Anritsu, a leading manufacturer and supplier of electronic measuring instruments. So by this, I mean your optical measuring instruments, your OTDR testers, bit error rate testers, transport internet testing, wireless communication measuring instruments, signal analyzers, vector network analyzers, and signal generators. Yes. So for today, we have an expert from Anritsu who will be doing a small presentation on 5G network field testing. And the webinar will be recorded and will be sent to all attendees. So for any questions, please feel free to drop them in the Q&A section, and our Anritsu expert will also have a chance to respond to them in our follow-up email. Yeah, so I think on that juncture, I'd like to hand it over to Marwan. Marwan, please take the stage. Thank you.
Thank you, Ronald, for this nice introduction. My name is Maran Bardisi. I'm the business development engineer at Anritsu. And today we have this webinar regarding 5G network field testing, where I will be presenting what are the different challenges when it comes to 5G network field testing, and of course, what are the solutions that we at Anritsu have to cover those challenges. So to start with the agenda of today's webinar, so I'll first highlight what are the different 5G challenges, which would basically as with regards to base station installation and maintenance. And after discussing every challenge, I will be presenting with what are the solutions regarding each one. So to start with 5G, what are the three pillars of 5G? Where there are three pillars. The first one is the ultra high reliable, low latency. This is of course important for many different applications, which include, for example, self-driving cars, autonomous driving, of course, in order for the automotive cars to drive, without any accidents, without any incidents. The communication between them and the network, of course, needs to be at a very low latency. Other applications include robotic arms and either warehouses where a worker, for example, would be using a robotic arm to maybe lift some boxes, some crates, and so on. There are some applications as well for remote surgeries. I'm sure we've seen many of those happening. So all those require a relatively reliable low latency network to ensure there are no accidents. The second pillar is, of course, the faster and larger capacity. So we're always moving towards higher quality video streaming, so from 4K to 8K. And of course, as the quality increases, we require more bandwidth and more speed to cover those. And then finally, of course, multiple connections, IoT. With that, every device needs to be connected, and with the evolvement of 5G, a lot of more devices are coming online. When you talk about smart homes, smart cars, everything is becoming smart, everything is becoming deployed directly in the network. And of course, they all need to be synchronized and talking to each other. So multiple connections is the third pillar of 5G. Now, these three pillars present us with different challenges. And of course, they need to be examined and they need to be discussed, which is the point of this webinar. So what are the challenges that were presented to us? Well, the first one is the performance check at installation. So when we're talking about building or constructing a base station, performance check is very important. It's one of the challenges. The next one is, of course, interference. Interference is always there, and with 5G, with multiple connections, interference is always an increasing problem and needs to be sorted out. Then finally, the network latency. So the latency of the network and the network performance itself needs to be tested properly in order to ensure that there are no problems. So these are the challenges that I will be discussing today, starting with the performance check and at the installation. So let's take a base station that is, to be constructed. We're starting with the base station down in the room. From there, we have some jumper cables connected to the surge arrestor. From there, up the up the tower, we have the feed cable, which is connected to the jumper cable, and finally, it's connected to the antenna. Where the challenge rises is we need to make sure that the power output from the antenna is at its maximum or as close as it can be to the power input. So from the base station, we're supplying the power input PI, and we need to make sure that the power output is as close as it can be to power input. Where is the power lost? Well, the power is lost in multiple locations. The first one is of course the attenuated power. So the cable that's connecting the from the base station to the antenna, the feed cable itself, could have losses, and this needs to be checked, of course. Other sources of power loss is, of course, power that is reflected at each and every point of connection due to different, of course, reasons. That could be a bad or a loose connection, or even could be an impedance mismatch between both ends. That will cause some of the power to be reflected back. And if this power gets too much, the power could actually, the signal that's reflected could actually affect my transmitter. One other source of power being reflected is, of course, extreme bends in my cables. So this could also increase to how much power is being reflected back. And then finally, of course, overall decrease the power output. And the power output, of course, is the main, I would say, contributor to the cell coverage. So the less power there is, the less coverage there is around the base station. And of course, the less users that can be connected, the more costly it will be to run the network and so on. So this is the objective. The objective is, like I said, to make sure that the power output is as close as it can be or at its maximum input, maximum output. And this is why what's essential to do is line sweep. And for the next slide, I will explain what are the typical measurements that you can expect from a line sweep. But first, to understand what is a line sweep. A line sweep is essentially a test to measure and verify the system performance. So the line sweep will enable me to understand how much power is being delivered right at the antenna, how much power is lost throughout my entire system, and if there is any faults, if there is any high power that's either being lost or reflected back, line sweep test will enable me to actually locate it throughout my system. So what are those typical measurements? Well, the first one is return loss, and this is basically measuring the power that's reflected back. It's a measurement that's done on a device where we measure the reflected signal to the incident signal or the signal that is entering the system. It's measured in dB, and uh, this return loss gives me an idea of how much power is returned back or gets reflected back. Like I said earlier, this could be either due to extreme bends and breaks in your line, or it could be due to bad connections or non-secure connections between the adapters. The second one, of course, is cable loss, and this is the power that's attenuated. It's also referred to as insertion loss. So sometimes cables have extreme losses throughout the line, and this, of course, loss results in lower performance. And when you talk about the KPIs of a network, the KPIs as well uh, are relatively low. You start facing something like dropped calls or a lower data rate and so on because the power output is not uh, as its optimum performance. And then the final one is distance to fault. So assuming I know that there is high losses, or I know that there is high insertion loss, distance to fault is a measurement that allows me to understand where exactly along my line. It allows me to understand where is this location. When distance to fault is applied properly, that it will give me an estimate of where this high loss or where this high reflection is happening in my system. But furthermore, the other problem that we sometimes face, especially due to loose connections, is PIM. So PIM is also another problem that we face in the network. And to understand, PIM stands for passive intermodulation. In short, or in its simplest form, PIM is a type of interference. It's new frequencies that is generated, and they get intermodulated together, and they're generated at specific intervals. And these, of course, cause many problems. These new frequencies that gets generated into the system cause many problems, like dropped calls, increasing the noise floor, or even slower data rates, and so on. And PIM happens when a system is non-linear. And further on along this presentation, I will explain what is meant by non-linear and how they can be fixed. But first, to understand exactly what is PIM, if we take two transmitters, these could be two different carriers from two different technologies, or two subcarriers, whatever it may be. If we have two carriers in a system, and there is nonlinearity along my network, these two carriers will generate what's called as PIM, and these little signals that are generated as are causing, of course, this interference. There are two traits that needs to be noticed here. The first one is that as we increase in order, the power or the magnitude of each one gets less, but its bandwidth increases. And this is due to the nature of PIM and how it's calculated. We can see that with every order of magnitude, the PIM is increasing. And the problem lies when the PIM starts interfering with my uplink station. And that's why, because of this, I would have to increase my noise level, and the user, of course, would start experiencing dropped calls or slower data rates and so on. Now, what causes this PIM in my system? This is caused, like I said, by nonlinearities. And what are the nonlinearities? Nonlinearities have a lot of problems. So, for example, when we talk about loose connections, or maybe metal alongside the antenna, even if the connector itself is not clean, like for example, there are some metal flakes or there is some rust, there is a loose connector. All those objects or those nonlinearities cause PIM, and this is what we see in this slide here. So if you look at this picture of a spectrum, here we have the downlink, and in my uplink I can see all those the intermodulation carriers, and this is PIM. And if this is causing that my noise level to be very high, or like I said, this would cause the users to experience dropped calls, slower data rates, and so on. So PIM is an ongoing problem that needs to be tested for, that needs to be fixed in my system. And this is what we offer from Enritso. So what is the solution? Well, the solution is simple. We need to run line sweeps to verify the losses, but we also need to run some tests, and they always go hand in hand. So starting with line sweeps, well, the process is very simple. You need to connect the system. You need to verify any return loss. And if you happen to find some losses in your system, well, that's where you do the DTF, the distance to fault, to understand where exactly this problem is. Then you can go and repair it, run the system, run the test again to make sure that everything is good. But then once that step is done, the next step would be to run the PIM test. And the PIM test, of course, there are two types of PIM that needs to it. So we have the static versus PIM. So once I find that there is PIM in my system, very similar to running line sweep, there is this DTP, which is distance to PIM. Once I find out exactly where this PIM is being caused in my system, then I can go repair it, run it again. And the next step would be to do the dynamic test versus PIM, where I would manually go along my line, change anything, and monitor the PIM tester on the other end to make sure that there is no PIM. And finally, we run the final tests, and we're done. So this is simply the process. And what are the solutions we have for this? Well, for PIM, we have the PIM master, and the PIM master works in a very simple manner. We inject two known frequency carriers into the system. So F1 and F2, I know what their frequencies are, and I start monitoring on the third IM product. So this is what the PIM does. All you need to do is just simply do the connection, and the device will input into the system to inject two known frequency carriers into my system, and it will start monitoring. And of course, if I see at any point that there is a relatively high PIM, then I can go along my line with distance to PIM, and I can investigate exactly where the problem is. These are the different measurements that come from the PIM master. So we have the PIM versus time. There is the swept PIM as well. DTP, which is distance to PIM, which gives me exactly after how many meters, for example, is my PIM happening in my system. And of course, there is the time and spectrum view of the noise flow. There are different frequency options, and each one of those is a separate device. So depending, of course, on the technology that you are testing, you would select one of the frequency options that we have and do that test. For line sweeps, we recently introduced the new Site Master. Now, the Site Master is a very well-known brand from Enritso, and it's about time it got an upgrade. So now we introduced two new Site Masters, the 2085 and the 2089. Both of them are essentially the same, except that the 2089 also features a spectrum analyzer, a very powerful spectrum analyzer, might I add. And I will talk about the spectrum analyzer features of this one in the next section of my presentation. But just to give you some highlights of the site master. So the site master, we have two frequency options, so either 4 or 6 gigahertz. It has a very fast sweep time, so that's 350 microseconds per data point. It's designed for the field, so the battery lasts you a full workday, so about up to 9 hours. The screen is IK08 rated, so it can withstand impact, and it can also, with the soft case, it can withstand water splashes and dust as well. And these are the different measurements that you can expect from the site master. So you can do your reflection measurements, your transmission measurements, the distance to fault, TDR measurement, even filter, and a power meter included into that one as well. The next challenge to consider is, of course, the influence of interference. Now, interference is always an ongoing problem, and there are many different signs of interference in my system. The first indicator I would say could be because some noisy analog links. So when I'm monitoring the spectrum, I would see some noise. If there is if users are reporting some lower throughput, if I see that the noise floor is relatively high, or the SNR or the overall receive tower is not as it should be, then I have interference in my system, and there are different types of interference that needs to be tested. So it can be an on-channel interference, so different cells using the same frequencies interfering with each other. There is it could be an in-band interference, so in-band interference could be happening from other carriers operating at the same frequency, operating in my RX band. So it's not exactly in my in the same channel, but it's in my overall receiving band, and it's causing, of course, interference. Impulse noise, which could be due to either railways, it could be due to bakeries nearby, or welders, emergency vehicles. All those factors add to my impulse noise. There is harmonics. Of course, harmonics is due to the natural behavior of amplifiers. With the way they work, they produce some harmonics, and if these harmonics are not filtered out properly, they can cause some interference in my system. PIM, which is a type of interference, like I said before. Then finally, it also could be an intentional type of interference. So that's your frequency scramblers, your frequency jammers, and so on. Now, interference hunting, of course, is a very wide topic, but in order to understand how to do interference hunting, you first understand what is my interferer, what is my source. So it's very important to characterize your interference. So I need to look at what is the frequency of my interferer, what is the bandwidth or the overall shape or the power level. It could be possible that this interference is coming from another carrier, so there is a chance to, if there's a chance to demodulate this interference, I can try to do that. There is also the option of demodulating the FM, so I could even listen to that interference, see any type of behavior around it. It's also good to monitor how this interferer changes with time. Is it always at the same frequency? Is it pulse? Is it frequency hopping, and so on? So it's always important to get a clear idea of what your interferer is, to be in order, of course, to capture or go directly to the source of interference. Now, what are the tools that you need for such a job? Well, it's simple. You need a wide enough spectrum analyzer in order to capture its entire behavior. If the spectrum analyzer also has RTSA, which is real-time spectrum analysis, this is a very important tool, because it makes sure that we do not miss any of the behaviors of the interferer. I can monitor it in real time, see, and be up to date with any changes that happen. And then finally, a spectrogram gives me a visual cue of what's happening through time. And just for your information, further on, I will show you exactly what an RTSA and what a spectrogram should look like if done properly. So what are our solutions for this? Well, we have the field master range. We have three little brothers. So we have the 2070, the MS-2070A, the MS-2080A, and finally the Pro version, the MS-2090A. Each of them has its own features. Each of them has its own, I would say, users. For now, I will talk about the Fieldmaster Pro, the MS-2090A. Of course, if you'd like to know more about this or any other product, please feel free to reach out. So the MS-2090A can go up to 54 gigahertz in frequency. It features the real-time spectrum analysis with a bandwidth of up to 110 megahertz. It has very low displayed average noise levels, so up to minus 164 with the preamplifier on. So it's very sensitive to even the lower power signals. So even no matter how low in power my interferer is, I can very easily go and see it and detect it. It can demodulate 4G and 5G, as well as WCDMA, and of course AM/FM demodulation. It has IQ capturing and streaming, so I can capture the IQ data for further analysis on an external software, and I can stream this IQ data even in RTSA to an analysis software, and I can look at all the vector error magnitude and so on. There is EMF measurements, a pulse analyzer, and also it features interference hunting with the MA2700, which I will talk about in the next coming slide. This is, just for your information, how the RTSA and how the spectrogram looks like on the device. So on the left side on this picture, this is an RTSA capture of a 5G carrier. And the RTSA is clearly showing me the SSB, the signal synchronization block. This SSB would not be visible on a normal spectrum that doesn't have RTSA. The RTSA displays the information in a different way other than your normal trace on a spectrum. And then we have also the spectrogram. So this spectrogram is an example of a Bluetooth signal hopping around three main anchor signals. And you can clearly see it, hopping from one to the other. And again, this would not be possible without the spectrogram as well. The ultimate tool for, of course, interference hunting is the MA27A interference hunter. So this is a handheld device where you connect an antenna to it, and it features a trigger button, which is what we use to directly lock on the source of interference. This is how the setup would look like. So you have the shoulder harness, and the idea is that you leave the device free to use with your hand, and you use the interference hunter with its built-in compass, and the device will actually show you on the map an estimate location of where this interference source could be. The Field Master really is the ultimate platform for interference hunting. So we can use it with a mag mount antenna mounted on a car and do sort of mobile interference hunting in the car. So it will give me sort of this heat map of an estimate of the location. The device using the MA27A interference hunter will give me an estimate on the map of where the exact source of interference is. And I can also use it to generate a polar plot. This polar plot allows me to see if there is more than one source of interference. So in this example, we can see two main sources. One is coming from this direction, the other one is coming from that direction. Add to that, of course, the ability of capturing the IQ data and spectrum recording and streaming this IQ data in real time. We can also do modulation quality measurements. We can export this IQ data into a software, and the software will then give me all the vector signal analysis capabilities like the eye diagram, the vector error magnitude, and so on. I can even replay this data for further analysis later on. I can demodulate a 5G or a 4G or a 3G tower and look at the modulation quality measurements. I can also do EMF measurements with the EMF antenna. So it really is an all-in-one solution for interference hunting. The last problem or the last challenge that we face with 5G is, of course, the network latency. Now, when I think about latency, I like to think of this little graph here. So this is just an example, of how a network, just a simple diagram of how the network behaves when every aspect of it, every component is perfectly synchronized. There are no accidents. All those components, of course, except for the human beings walking, all those components are communicating together. They know exactly where everything is, where everything should be, and it's all a very nice, seamless flow of traffic. And of course, this presents with a lot of problems. So when we talk about 5G, 5G deploys eCPRI, which is Ethernet or CPRI over Ethernet. And the main idea here is that we are no longer using the GPS directly onto the base station. So instead, all those base stations are using what's called the PTP network. And the PTP network gets its clock or gets its information from a grandmaster clock that's connected, or it can see the GPS directly. And all the data or all the time information is then transmitted through packets throughout the network. And this grandmaster clock can really be deployed anywhere along the network. It's no longer at the base station. It's usually closer to data center. And the PTP network transmits the time information to my base station. And what does that, of course, present? It presents, well, really two problems which need to be tested. So when we talk about latency, of course, just is how fast the information is transmitted from the data center to the base station. And the maximum delay that's allowed is 100 microseconds. So that's for the latency. But one other aspect of this is the synchronization. So the synchronization is not about how fast the information is traveling, but how close are, for example, assuming I have more than one base station, I need to make sure that both base stations are receiving the information at the same time, that the information at this base station is the same as the information as this base station, and so on. So network synchronization is important. At the beginning, the base station used to have direct access, to the GPS, and it got its clock from there. But in some cases, it's not always physically possible to connect an antenna that can see the GPS, which is why now the base stations get its information from the PTP network. And this is why the network latency and the network synchronization need to be tested properly to make sure that the performance of my network is at its optimal condition. What are the solutions we have for this latency and synchronization? Well, we have the MT MT1000, the Network Master Pro. This is sort of an all-in-one network tester. This device can measure the synchronization of the mobile network, and it can also test the PTP protocol itself. It can really test anywhere along my network. It also, this device is module-based, which I will explain in the next coming slide. So really, this device can do all of your transport testing. So whether it's Ethernet, OTN, fiber, and so on. There is the benchmark tests as well. And the ones that I will present in the coming slide is, of course, the PTP and the sync E and the latency tests. So this device, like I said, is a module-based device, and depending, of course, on your use case, the specific module will be applied. So there is also an OTDR module. So not only I can test the data, but I can also test the fiber itself with the OTDR module for any breaks or any losses along my fiber. Now, why do I need such a device to test latency? I'm sure everyone already knows that there's a way to test the latency of any network where I use this ping command where I send the information and receive it back. But in reality, this is not really the latency. What we measure in this case is the round trip delay. And the problem with this is two things. First thing is the ping information is not real traffic. It's a few bytes of information that's transmitted along my network, and the server is usually programmed to assign this to a higher priority, and it will transmit this information back. The second problem with testing the latency this way is that we're assuming that the path that the packets take from my device to the server is the same as the path that this from the server back. And what I would do, I would simply divide this round trip delay by 2 and get my latency. But in reality, that's not really the case. The proper way to test the latency is, of course, to have two clocks perfectly synchronized on both ends. And the test on the MT1000 is done using real IP traffic. It's not using the ICMP load. And that way I will be able to accurately measure the latency from one end to the other, as opposed to testing the ping, which is in reality the round trip delay. The next phase of this testing is, of course, the PTP and the sync E test. So the MT1000 can test the PTP, which is the protocol. So the MT1000 can connect to the grandmaster clock, to the boundary clock, or to the transparent clock, and it can either act as a manager and it will test the actual protocol, the functional test of the protocol of each clock to make sure that conforms to the standard. And the next part of this is, of course, the synchronization test or the time error test, where the MT1000 will get the PTP information from the PTP network, and it will compare this one with its own internal clock, which gets the reference directly from the GPS, and it will measure the synchronization between both ends and make sure how that the network is operating at its optimal condition. To summarize everything we talked about so far, so we've experienced or we've explored three different challenges in the base station installation and maintenance. So that is the performance check at installation, there is the influence of interference, and then finally there is the network performance for latency and synchronization check. For performance check and installation, there are of course many challenges like the cable loss, the reflected waves, impedance mismatch, and of course the PIM. And for that, we have two solutions. We have the PIM tester to test for the PIM, and we also have the site master to test for the cable and turn loss. For interference, we have multiple problems that happen because of interference. So it could be declined data rates, interrupted communications, or an increased noise floor. And for that, we have the field master family, which really is the perfect tool for interference hunting with the RTSA, with the low noise floor, with the very wide frequency range and capture bandwidth. We can really zoom in and locate very precisely where this source of interference is. And of course, for the network performance, we need to test and ensure that the latency and network synchronization is up to standards. And for that, of course, we have the MT1000 to test the latency, test the functional BTP protocol, and of course, test the synchronization of my network. Thank you, everyone, for attending this webinar. Do you have any questions, please? I think we do not really have any questions. So, Ronald, back to you.
Yeah, thank you, Marwan, for that very insightful presentation. We appreciate. Yeah, I think so. If there are no questions, I believe we can maybe we can end there. But please, if anybody has any questions, please type them there in the Q&A section. But if not, we'll always be available to answer any questions that you may have later. As mentioned before, the recording of this webinar will be sent to all you attendees. And our lines are open. Yes, we hear from Amotech and Ritsu will be open for any further inquiries or clarifications. Yeah, I think on that juncture, maybe we can end the webinar. Maybe a vote of thanks once again for everybody for making time to attend this webinar. Eric, might you have anything to say?
Thank you, Ronald. Mine is just to reiterate what you've already mentioned. Many thanks to the attendees. I know what we've been experiencing here in Kenya. You guys taking time to join us for this webinar. We don't take it for granted. Also, many thanks to Marwan for such an insightful presentation. We shall be having a seminar next week. In case you're interested to join us in the seminar, it's a physical seminar next week on Wednesday. In case you're interested to come, because now the trainers will be, whatever the trainers have highlighted in this session will now be discussed at a greater length. So might you be interested in attending? Please reach out to us. We still have slots available for you. Having said that, once again, many thanks for joining us in this session, and wish you a good day ahead. Back to you, Ronald.
Okay, thank you, Eric. Yeah, so yes, I think that marks the end of the webinar. Please feel free to leave at your leisure. Have a great rest of your day. Thank you.